I will be continuing with the determinants. As a recap to my last lecture, we define the determinants first. Determinant of a square matrix A is a number denoted by determinant A. Actually, we associate a number with a given matrix, especially a square matrix, then we say that determinant is uniquely associates a number with a square matrix. We have discussed some schemes for computing determinants of square matrices of order 2 or 3, like if I have a second order matrix, then its determinant is computed as A11 A22 minus A12 A21, while for a third order determinant is calculated as product of A11 A22 A33 A12 A33 A31 A13 A21 A32, these are summed up, and then we calculate the sum of terms A13 A32 A31 A11 A23 A32 A12 A21 A33 and take the difference. But this type of definition cannot be continued for high order determinants. So, we define determinant for nth order square matrix as determinant A is equal to signum of the permutation sigma and the product of I is equal to 1 to n of ai ji. Now, this is explained with a 4 by 4 matrix, and we say that we calculate the product of terms like A11 from the first row first column, A24 from the second row fourth column, A32 from the third row second column, A43 from the fourth row third column. The idea is we will take only one term from each row and column. This way factorial n permutations are possible. We calculate this product of all such terms and then take the sum. But then we define determinant A as summation of minus 1 raised to power j plus I aij minor mij. Mij, this actually denotes the minor, this we have defined in the last turn, and this definition can be applied to any row or any column. This way we define a determinant in terms of lower order matrix determinants. This is true for ith row, this definition can be applied to any row, while this definition can be applied to any column. The result is determinant A. Now, we have further defined cofactors aij. For the idea is here we are having minus 1 j raised to power j plus I mij. So, we absorb this term with this minor and we define aij is the cofactor of aijth element of the matrix A. So, we define determinant A in this order, in this particular manner where I varies from 1 to n, and if we consider column wise expansion, then we can take this definition and j varies from 1 to n. After that, we have discussed some properties and we have proved these properties. These properties actually help us in evaluating determinants more conveniently. Like if the elements of a row are 0, then determinant A is 0. We need not to compute all the terms which we have discussed. We simply say determinant A is 0 if any row or column it becomes 0. Similarly, if the two rows are identical, then determinant A is 0. You do not have to calculate all the minors. If two rows are proportional, then determinant A is 0, and if two rows are multiplied by k, then if a row is multiplied by k, then k times determinant A will be the value of new determinant. If interchange of two rows occurs, then determinant is multiplied by minus 1. So, determinant A becomes minus determinant A after interchanging of two rows. Similarly, we had applied elementary transformations to corresponding matrices, and then we see what is the relationship between the determinant of the matrix before applying the operation and after applying the operation. So, before applying the operation it is determinant A, but when we change it the determinant remains the same. But if we apply this elementary transformation, then determinant obtained after applying this transformation is divided by k. But this elementary transformation will not change the value of the determinant. Now, these transformations actually help us in evaluating the determinants more easily and with less computational effort. Now, let us try to have some idea about the computational effort involved in the matrices, because matrices are used extensively in engineering and scientific applications. So, let us have some idea about the computational effort involved in it. Cofactor, if we use the cofactor expansion to evaluate the determinant, then the computational effort is of the order of factorial n. This factorial n is coming because we have seen that for a determinant there are factorial n type of products possible. They have to be multiplied, they have to be added and subtracted. So, the computational effort the computational effort employed will be of order of factorial n. Now, you will be having a better idea if you try to see it on a system when n is equal to 1, 2 and so on. So, if n is equal to 5 and we are evaluating a determinant on a machine which can compute 10 raised to power 3 operations per second, then for n is equal to 5 the computational time will be of order 0.0003 seconds. Okay. If we increase the matrix size to be 10 by 10, then the computational effort required by the machine will be 10 seconds. And if you further increase the size of the matrix to 15, then the determinant will require 4 into 10 to the 6 seconds of computer time, and this amounts to be 40 days. If you further increase the matrix size to 20, then the huge effort is required and the computer time will be 7 to 10 to the power 6 seconds, which comes out to be these many years. And if you further increase it say to 25, then we require approximately 10 raised to the power 12 years to compute a matrix, to compute the determinant of a matrix of size 25. Now, engineering applications require large matrices to be handled, and we have to be computing determinants of higher orders. So, if this is the scenario, then it will be difficult to use determinants in practice. So, we will not be using cofactor expansion, rather than we will be using other method which is called the triangularization method for computing determinants. Let us first compare, let us see how the computation effort in this case will be. So, if we in this particular case the computation effort is of order 2n cube divided by 3. So, this is the order of the computational effort required in computing determinants using this method. So, this is the table for I am giving the values for 20, because if we are using triangularization method, then for n is equal to 20 the computational effort will reduce to 0.005 second. If you compare it with the earlier case, then this is very small, and when we increase n to be 25, then 0.01 second will be required to compute the determinant by this particular method. So, although the method is the same, definition cofactor definition remains the same, but triangularization method reduces the computational effort tremendously. For 4 or 5 order matrices, the effort may not be very may not be compared, or if we are doing hand computation, then maybe we find that triangularization method is not so is messy, but for higher order matrices things are really more comfortable when we use triangularization method. Now, after this we will be discussing some more properties of determinants. They will be helpful in applying determinants and matrices to engineering problems. Now, for this let us consider a matrix n by n square matrix consisting of A11, A12, A1j, A1n elements in the first row, A21, A22, A2j, A2n in the second row. This is the ith row of the matrix, while this is the last row. This indicates that there may be number of rows in between, and this also indicates there may be number of columns in between here or here. Now, the matrix, the determinant B is the determinant of this matrix. This matrix is the same as this matrix, the only difference is in the jth column. So, A11 in the B matrix is the same as here. So, all rows and columns are same except this particular column. So, the determinant C is the same as determinant A, but the difference is in the jth row. The jth row is having A1j and B1j, the sum of the two. In fact, the jth column of A and jth column of B are added to give the jth column of C matrix. So, if we define C matrix in this particular manner, then Cik is equal to Aik is equal to Bik for all k not equal to j, and Cij is equal to Aij plus Bij for jth column. Then we have a result which says that determinant of C is equal to determinant of A plus determinant of B. Let us prove this result. We can expand the matrix about jth column to get the determinant A. So, this way we write down determinant A as summation I is equal to 1 to n Aij multiplied by Aij, Aij being the cofactor of Aij, that is, this is the matrix A. So, we have obtained determinant A about this column. Same thing can be done for B. Now, one can observe that Aij is equal to Bij. Why? Because Aij, the cofactor of Aijth element, is obtained by deleting this column and this row. Bij is the cofactor in the B matrix by eliminating this column and this row. But this is the only difference in A and B. So, this cofactor Aij will be equal to Bij, and this means A plus B, determinant A plus determinant B is equal to Aij plus Bij, this is taken and Aij is common. So, this is equal to Aij plus Bij multiplied by Aij, and this simply means that determinant A plus determinant B is equal to this determinant where the jth element is the sum of the two. Now, this is nothing but what we have, that is the C matrix. This simply means the determinant of A plus determinant of B is equal to determinant of C. Now, it gives me a feeling the determinant of A plus determinant of B will be equal to determinant of A plus B, but actually it is not, because if I add two determinants A and B, the result will be 2 times A11, 2 times A12, but this will be A1j plus B1j, and this will also be 2A1n. So, that means A plus B is not equal to determinant of A plus B. That means this is what do we mean by this? This simply means that we first add the matrices and then take the determinant. So, if we first add the matrices, so this is the resultant matrix, and taking the determinant will be getting this. Since the elements are different, then this, that means A plus B is not equal to determinant of A plus B. So, this is what we have, determinant of A plus determinant of B is not equal to determinant of A plus B. Now, this I can explain, this I can verify with an example also. So, if I have a determinant A as 1 2 2, 1 4 2, 0 1 3 and determinant B as 1 1 0, 1 2 0, 2 2 3, then the determinant C will be, first column is copied as such, third column is copied as such, but the second column is 2 plus 1 3, 4 plus 2, 6, 1 plus 0, 1. So, determinant C is this. So, let us calculate the determinants. The determinant A is first column, first element, first 1 into 12 minus 2 minus, I am expanding about this, 6 minus 2, and I can expand about any row or any column, but since this particular matrix has one element 0 in the first column, so I will prefer to compute determinant by expanding about the first column. The idea is this way I will be performing less computation as compared to this column, this row or any other column. So, I will be computing only these two terms, not the third term. So, this gives me the result as 6. As far as the determinant of B is concerned, I will use the same column for evaluating determinant, and it comes out to be 1 into 6 minus 0 minus 1, and it is 3 minus 0. So, the final result is 3. Similarly, the third determinant 1 into 18 minus 2 minus 1 into 9 minus 2, and that gives me 9, and one can check that determinant C, which is 9, is equal to determinant A plus determinant B, which is 6 plus 3. So, we have verified the result, but if you compute A plus B determinant, then it will not come out to be same as A plus B. Let us see this. We have already computed A is equal to 6, we have computed determinant B as 3, we have computed A plus B as 9, but if you have to compute A plus B determinant, then this comes out to be 2 into 36 minus 4 minus 2 into 18 minus 4, that gives me 64 minus 28, and finally A plus B is 26. Clearly, A plus B determinant is not the same as A determinant plus B determinant, and that proves. So, in general this result is not true. In fact, if we have to add this, and if the some rows or some columns are identical except one particular row, then we have the result given by earlier theorem. If we can generalize this, then alpha A plus beta B is not equal to alpha A plus beta B. Actually, it is very surprising that this result does not hold for addition. So, this is a linear property, this must hold for determinants, but we have verified that this is not true for determinants. This is very surprising, and one has to be very careful about it, that alpha A plus beta B is not equal to alpha A plus beta B. So, that is the basic difference between determinants and the numbers. But if we have two matrices A and B and of order, they are of order m, then the product AB and its determinant is equal to determinant of A into determinant of B. So, this is not true, this property does not hold for addition, but this property holds for determinants. So, here one has to be very careful. The determinants are applicable only to square matrices. So, it may happen that AB is a square matrix, but A and B are not square matrices. So, in that case determinant of like in this case A is m by k, B is k by m, AB will be m by m. So, AB is a square matrix, its determinant is possible, but if you want to apply this, then determinant of AMK is not defined, determinant of B is not defined. So, this will not be defined for this set of matrices. This property is true only when A and B are square matrices of same order, say m. So, in this case determinant AB is defined, but determinant A and determinant B are not defined. So, this property is invalid. Now, to prove this, actually the proof of this property is really very complex. I will first try to prove it for m is equal to 2. So, for m is equal to 2, let us consider two square matrices of order 2, A as A B C D and B as X Y Z W. Then determinant A is equal to A D minus B C, while determinant B is X W minus Y Z. However, the determinant A B will be, first take the product and then take the determinant. This means the product of these two matrices, the first row first column element will be A x B z. This element is obtained by multiplying A b by y w, and this element is C x d z, and finally the last element will be C y d w. So, this is determinant A b. So, let us see what is A multiplied by B. So, if we expand A b, then it will be A x plus B z multiplied by C y plus d w minus A y plus B w into A y plus B w. If you further expand, then A b is equal to A d minus B c multiplied by X w minus Y z. Now, we will try to match the two things. So, we start with A d minus B c X w minus A d minus B c y z by expansion, and then A d X w plus B c Y z minus B c X w minus A d Y z, and here I am trying to add and subtract certain things so that the final result can be obtained easily. So, A x d w is with me, I will add C y A x and subtract C y x a. Similarly, I write down B z C y plus d w, B z C y is with me, I subtract B z d w and add B z d w, and then these two terms. Now, we can adjust these quantities and we can write down A x plus B z into d w plus C y minus C x A y plus B w minus d z B w plus A y, and that gives me the final result as this. So, determinant of product is equal to product of determinants. Now, as far as proof for general n, that is that cannot be done in half an hour. So, this requires lot of computational effort. So, I leave this as an exercise for the viewers, they just try and check that this result hold for other values of m also. Now, we have computed determinants of number of matrices. Some results may be of worth noting, that is the determinant of identity matrix is 1. This can be easily obtained for I 3. In general, I n is equal to 1. This identity matrix happens to be a diagonal matrix and all the diagonal elements are 1. So, I n will be 1, and then of course, we have already proved the result that A b is equal to determinant of A into B. So, we can use it repeatedly to give the result as the product of k matrices. Of course, they have to be square matrices, they have to be of same order, then this is equal to product of k determinants. One has to be sure that all the determinants are of same order, all the matrices are of same order and they are square, only then this result is valid. What we can do is, we first take this term multiplied by A1. So, it is A1 into determinant of this, then we can apply the same result to this considering A2 and rest of the terms can be taken together. So, we will be having A1 A2 into rest of the terms, and this can be repeatedly applied to give the final result. There are certain remarks. One thing is that for product of matrices AB is equal to 0 does not imply that A is equal to 0 or B is equal to 0. This is the result which we have seen when we were discussing determinants, that it is quite possible that A and B, none of them is 0, but their product AB is 0. Now, this is not true for determinants. Like if I have determinant of a product is 0, then this simply means that either determinant A is 0 or determinant B is 0. This can be proved very easily, like you can say that determinant of this product is equal to determinant A into determinant of B, determinant B, and this simply means if determinant A is 0, then what are determinant A and determinant B? They are simply numbers. So, one of the two numbers have to be 0. So, either we will have determinant A is 0 or determinant B is 0. So, this result was not in general true for matrices, but this result is true for their determinants. Similarly, this is another remark, the product of matrices AB is not equal to BA. We have proved that the product of matrices is not commutative, that is AB is not equal to BA. Of course, it is important that AB and BA should be of same order, and these two products are possible. But if you consider the determinants AB of a square matrix A and B of order m, then determinant AB is equal to determinant of A into determinant B. The same way, determinant of BA is equal to determinant B into determinant A, but what are determinant AB, determinant B and A? They are simply numbers, and the numbers can be commutative. So, determinant B into determinant A can be written as determinant A into determinant B, and that makes determinant of AB is equal to determinant of BA. So, this is again in contrast with the theory of matrices, where AB is not equal to BA, but for determinants AB is equal to BA. We have seen that if the matrix is a diagonal matrix, then one can very easily calculate the determinant by simply multiplying the diagonal elements. Let us see what happens if the matrix is a block diagonal matrix. By this I mean to say that I have a matrix of order say 4 by 4, and this can be partitioned into sub matrices, like this can be partitioned, and this is a sub matrix of order 2 by 2, this is a sub matrix of order 2 by 2, they lie in the diagonal, and these are the matrices which are null matrices. I denote them by Z. So, let us say this is A matrix, this is B matrix, and this is null matrix. So, we will have A, B, Z and Z. So, if it is a block diagonal matrix, then how can we calculate the determinant? So, if let us say we have a 2 by 2 matrix and it is a diagonal matrix, then what will be? A is a simple singleton, B will be a singleton, Z will be 0, Z will be 0, and determinant of this matrix will be simply be the product of these two terms, that is A into B. But in this case I am having not a singleton, but I am having a matrix of order 2 by 2 or a matrix of order 2 by 2 as the B matrix. So, how we can calculate the determinant of this matrix? It may be noted that this I have taken for example. It may happen that this is of order 3 by 3 and this is of order 2 by 2. So, these null matrices may be rectangular, but these matrices have to be square matrices. Like we will have a 5 by 5 matrix. So, we may be having 3 by 3 matrix here and 2 by 2 matrix here. So, this will be a rectangular matrix and this will be a rectangular matrix. So, we will be having a block diagonal matrix A, B, Z, Z. So, how the determinant of this can be calculated? This I will show for C matrix, which is the determinant of A11, A12, 0, 0, A21, A22, 0, 0, 0, 0, B11, B12, 0, 0, B21, B22. Now, the determinant of this can be easily calculated. What I can do is I can expand it about the first column. So, it will be A11 multiplied by its cofactor plus A21 multiplied by its cofactor. This term will not contribute, this term will not contribute. That is the advantage of having zeros in the particular row or column. In fact, we select the particular row or column which will have some of the terms zeros. Now, in this case every column or row will be having 2 0 terms. So, it does not make much difference whether you use this column or this column, but for convenience I am using this particular column. Now, what is A11? A11 is a cofactor of A11. How we obtain A11? A11 is obtained by neglecting this row and this column, that means this particular determinant. So, this particular, to evaluate this particular determinant I will again expand by cofactors. So, for this I will consider this column. So, it is A22 multiplied by this determinant I know is B. This term and this term will not contribute. So, A11 is nothing but A22B. Similarly, A21 A21 that is cofactor A21 will be A21 into A12. Let us see, if we calculate the cofactor of A21, then this row and this column has to be deleted. So, the submatrix will be having A12 0 0 0 B11 B12 0 B21 B22, and again by cofactor expansion this will come out to be A21 A12 determinant B. So, determinant B is common in both the terms. So, B can be taken out and what we have is A11 A22 minus A21 A12. What is this? This is nothing but the determinant of A matrix, A11 A22 minus A12 A21, that is nothing but determinant A multiplied by determinant B. So, what we can say is, if we have a block diagonal matrix consisting of A matrix and B matrix in the diagonal, then the determinant of block diagonal matrix is nothing but the determinant A and determinant B. That means, if I have a matrix C having k block diagonal matrices or k block subdiagonal matrices, then we will be having determinant C as determinant D1 into determinant D2 into determinant Dk. So, one can generalize this result and this will be helpful in evaluating determinants of higher order matrices. Because of the matrix of cofactors of Aij of the elements of A is called the adjoint of A. By this I mean to say that if Aij is the cofactor of Aij, here the difference is, here is the capital Aij, small aij is the element, capital Aij represents the cofactor of the ijth element of the matrix. That is, adjoint A is A11, the cofactor of element A11 in the matrix A, A12 is the cofactor of first row second column element of the matrix A, A1n, and then we take cofactor of each and every element and then we take the transpose of it. That defines the adjoint of A, or adjoint of A is, transpose simply means the rows and columns are interchanged. So, I am writing A11 A12 A1n, the first row as the first column, A11 A12 A1n, and this is the second row, second column, which is here the second row, and the last row here will become the last column here. So, if I have the matrix A as this, then cofactor Aij is obtained as by considering a submatrix, deleting the ith row and jth column, and what we have is an n minus 1 by n minus 1 submatrix, take its determinant and then multiplied it by minus 1 raised to power I plus j, that becomes the determinant of, that becomes the cofactor of Aij. For example, if you have to find the determinant of the matrix 1 2 3 2 5 2 2 1 0 or 3 by 3 matrix, then you have to find out the cofactors of elements of this matrix. I call A11 as the cofactor of first element in the first row and first column. This I obtained by neglecting this row and this column and forming the determinant of this submatrix. Determinant of this submatrix is 5 into 0 minus 2 into 1, that means minus 2. So, A11 comes out to be minus 2. A12 is this cofactor of this element, which is obtained by neglecting this and this column, and what we have is 2 into 0 minus 2 into 4, that comes out to be A12 into 4, but actually this is determinant is minus 4, and I use the checkered pattern for getting the sign of the cofactor. The sign of cofactor here is plus here and minus here. So, this minus multiplied by this minus makes it 4. So, A12 comes out to be 4. Now, A13 is this determinant with plus sign. So, it is 2 minus 10, it comes out to be A13. Similarly, one can compute A21 as 3. A21 means cofactor of this element, which is 2 into 0 minus 3 into 1 multiplied by minus 1, that makes it 3. A22 is minus 6, which is 1 into 0 minus 3 into 2, it is minus 6, and cofactor of this element A23 is 3, 1 minus 4 with a negative sign here. Similarly, A31 is minus 11, A31 is this element, it is 4 minus 15, so it is minus 11. A32 is 2 minus 6 with a negative sign, so it is 4. A33 is 5 minus 4, comes out to be 1. So, what is adjoint A? A11, A21, A31, these are the elements which are in the first column, but when we are talking about adjoint A, they will become in first row, because it is a transpose of matrix of cofactors. So, what we have is minus 2, 3 minus 11 as the first row, 4 minus 6, 4 as the second row, minus 8, 3, 1 as the third row. So, adjoint of A is equal to this matrix, this 3 by 3 matrix. Now, on the basis of this, we have a theorem which states that A multiplied by adjoint of A is equal to adjoint of A multiplied by A. It is commutative, and not only this, is equal to determinant of A multiplied by identity. This is an important result. So, let us try to prove this. For this purpose, let us consider the product B as A into adjoint of A. Now, I denote adjoint of A as C. So, this B is equal to AC. To calculate B is equal to AC, what I have to do is I have to calculate the elements of the matrix B, which is the product of these two matrices. So, Bij, a typical element of this matrix B, is the product of this. So, what we have is Aij multiplied by Cij. This is equal to summation over k Aik Ckj. Now, this is from the definition of product of matrices. Now, what is Ckj? Ckj is the adjoint of A. So, this is nothing but adjoint is C is equal to adjoint of A. So, it is nothing but cofactor of Aik and its transpose. So, it becomes Ajk. So, Ckj is nothing but Ajk. So, this means Bij is summation of Aik Ajk over k. Now, to compute this, let us consider a case when I is equal to j. When we consider I is equal to j, then Bij is equal to summation over k Aik, because j is equal to I, and we have already proved that this is nothing but determinant of A. So, when I is equal to j, Bij is nothing but determinant of A, and this is true for all values of I from 1 to n. But what happens when I is not equal to j? To prove this result, let us consider Bij is equal to Aik, Ajk summed over k. Now, we define a new matrix D such that DRS is equal to ARS when R is not equal to I for all values of S lying between 0 and n. But DIS is equal to AJS for all values of n. That means the ith row of D matrix is the same as jth row of A matrix. That is how we define a new matrix D. Now, this means that Bij is equal to Aik, Ajk, this is what we have here summed over k is equal to Dik. Why I am using Dik? Because Aik is equal to Dik by the definition here, into Djk. Ajk is equal to Djk. What is Ajk? Ajk is cofactor matrix. So, this is the same as Djk. Now, one may notice that since ith and kth rows of D are identical, so all the determinants in all the cofactors Djk will be 0 because ith and kth rows of D are identical, and that simply means that Bij is 0 whenever I is not equal to j, and this simply means that Bij is equal to determinant A when I is equal to j, and it is 0 when I is not equal to j. By this I mean to say that the determinant B matrix will look like as this, where determinant A will appear in the diagonal, because for all the diagonal elements I is equal to j, and all the elements which are lying on the upper side of the diagonal or on the lower side of the diagonal, they are 0 because these are the elements where I is not equal to j. So, basically B is a diagonal matrix. So, if B is a diagonal matrix, then one can take determinant A outside, the number only, we can take it outside, and what remains here is nothing but the identity matrix, and that proves the result that A determinant adjoint A is determinant A times I. Similarly, one can easily prove adjoint of A is equal to A as the same as determinant AI. Now, this I leave as an exercise for the viewers to verify this. Hence, we can say that adjoint of A multiplied by A is equal to adjoint of A multiplied by A is the same as determinant of A multiplied by identity matrix. Now, on the basis of this, one can get some useful results regarding non-singular matrices. So, let me introduce non-singular matrix. So, we say a square matrix of order n is called non-singular if there exists another square matrix B of order n such that AB when multiplied by A multiplied by B is the same as B multiplied by A, which gives me an identity. In that case, I say that matrix B is an inverse of matrix A. So, if such a matrix B can be found, then the matrix A is called a non-singular matrix. The inverse of A is denoted by A inverse, A inverse. So, we say B is equal to A inverse, or we can say A inverse is equal to B. If no such B exists, then we say the matrix A is singular matrix. One can notice that this product is commutative. Now, we have a result which says that if determinant A is not 0, then A inverse is equal to adjoint A divided by determinant of A. Now, this actually later on, if once we prove this, then it becomes a formula for finding out determinant of A inverse. That is the importance of adjoint of A. Now, to prove this, let us consider the product A adjoint A, and we will prove that this is determinant A I. So, what we can do is we multiply this result, we have already established. So, what we can do is we pre-multiply it by A inverse. So, A inverse A is equal to adjoint A is equal to, this becomes identity, and adjoint A becomes determinant A, this can be taken outside, determinant A is equal to A inverse. So, what we have is adjoint A is equal to determinant A into A inverse, or A inverse, because determinant A is simply a number, you can always divide it by determinant A both the sides. So, A inverse is equal to adjoint A divided by determinant A. Let us take this example. A is equal to 2 by 2 matrix A C B D, then you have to find the inverse of given matrix A. For this we consider first the determinant A D minus B C. So, if A D minus B C is not 0, this is required. So, this condition is true, A D minus B C is not 0, only then we can find out the determinant, only then we can apply this formula, because if A D minus B C becomes 0, then this is not possible and inverse will not exist. So, A inverse is equal to adjoint A divided by determinant A, and this gives adjoint of A as D, adjoint of cofactor of A is D, cofactor of C is minus B, cofactor of B is minus C, cofactor of D is A, take the transpose, and what we have is D minus C minus B A, and then A inverse is equal to determinant A in the denominator. So, A D minus B C 1 upon A D minus B C multiplied by D minus C minus B A becomes the inverse of given matrix A. Let us verify that this actually is an inverse. So, what we can do is we multiply with A, and let us see it comes out to be an identity. So, if we multiply A by A inverse, we will have this product, and let us see this product, it is A D minus B C, which is 1. So, we will be having 1 here, but A C, the second element if you consider, it is A C with negative sign, then C A, they will cancel out, and what we have is 0 on the first row, second column. Similarly, B D minus B D, that gives me 0 as the element in the second row, first column, the right hand side, and then A B minus C and D A, that gives me 1 when divided by A D minus B C. So, what we have on the right hand side is the identity matrix. Similarly, one can prove that A inverse A is also identity matrix. So, viewer can actually perform this multiplication and get convinced that this is actually comes out to be an identity matrix. So, the result is verified. Now, this I have done for a 2 by 2 matrix, little more effort is required for a 3 by 3 matrix. So, if I have a 3 by 3 matrix A as 1 2 3 2 5 2 2 1 0, then its determinant is calculated as minus 18, 1 into this, 2 into this, and finally 3 into this, that comes out to be minus 18. Adjoint A is minus, this I have already done in one of the earlier exercises. So, this I have already computed. So, simply A inverse is 1 upon 18, 1 upon minus 18 as adjoint of A. So, that is A inverse. So, given A and A inverse which I have computed, one can verify that this comes out to be identity. So, if this row is multiplied by this, we will be having minus 2, 8 and minus 24. This comes out to be minus 18. So, the result is 1. This is 1, and you can similarly calculate other terms, and this comes out to be an identity matrix of order 3. Now, this is an important theorem which says that if a matrix is non-singular and if determinant A is not 0, the proof of this is that if determinant A is not 0, then the matrix is non-singular. This has actually two parts. If the determinant A is not 0, then determinant A inverse exists, and if determinant A inverse exists, then determinant A is not 0. Now, if determinant A is not 0, then one can find that determinant from the previous result that A inverse exists, because adjoint A can very easily be obtained. Is a matrix of cofactors. Determinant A is not 0, so we can divide it by determinant A, and in the earlier theorem we have proved that an A inverse is given by this result. So, if determinant A is not 0, then A inverse exists and the matrix is non-singular. However, if the matrix is non-singular, then its inverse exists such that A inverse is 1. So, if the matrix is non-singular and its inverse exists, then we have to show that its determinant will not be 0. So, let us consider A inverse is equal to identity, A inverse is equal to identity, because inverse exists and this is the very definition of inverse. So, let us take the determinant of this product. So, determinant of this product comes out to be 1, because determinant of identity is proved to be 1. So, we apply the product determinant A into A inverse, which comes out to be 1, and this simply means determinant of 2 is equal to determinant of 2 matrices, its result is 1. So, determinant A cannot be 0. That simply means that for a non-singular matrix, determinant A is not 0. Now, after proving this, one can take this result as a definition for a non-singular matrix. Previously, we were defining that non-singular matrix is the one which has inverse, but if now we say that if the matrix is having non-zero determinant, then it is non-singular. So, this can be taken as a definition of non-singular matrix. So, let A be a non-singular matrix, then A inverse is identity, or A inverse is equal to 1. So, A inverse is actually 1 upon determinant A. So, if determinant A is not 0, then A inverse is 1 upon determinant of A. So, if you know that determinant of A, one can very easily find out the determinant of its inverse. So, this result is helpful in that sense. So, let us illustrate this with this example. We have a determinant A as 2, determinant B as 3, then you have to compute the determinant of B inverse multiplied by 3A into 2B. So, what we can do is, we can write down the determinant of this product as determinant of B inverse into determinant of 3A into determinant of 2B. Now, determinant of B inverse is the same as 1 upon determinant of B. So, 6 into B inverse is nothing but 6 into 1 by 3, because determinant B is 3. Then determinant of 3A is 3 times determinant of A, determinant of 2B is 2 times determinant of B, that is how this 6 is coming. So, 3 and 2 is taken out. So, this result is equal to 6 times B inverse into A, determinant of A into determinant of B, that is 6 into 1 by 3 into determinant of A is 2 into determinant of 3, which is 3, and final results come out to be 12. So, if determinants are given, then one can compute this type of product.
Okay.
Now, I am considering the example in which you have to find out the value C such that the matrix A is singular. So, the matrix A is given as 3 minus C 0 3 0 C plus 2 0 5 0 C plus 5. Now, I will be using the theorem which I have just now proved, that the matrix A is singular if its determinant is 0. So, if determinant A is equal to 3 minus C 0 3 0 C plus 2 0 5 0 C plus 5 0. So, basically this matrix determinant is to be evaluated. To evaluate this determinant, one can expand it about this particular row. So, it is 3 minus C into C plus 2 into C plus 5 minus 0 into 3 times 5, that is 3 into C plus 2 times 5, that is this term, and to simplify it, it comes out to be minus C plus 2 into C plus 2 is equal to 0, and that simply means either C is equal to 0 or C is equal to minus 2 or C is equal to minus 2. So, for these values of C, the matrix A is singular. This matrix A is singular.
Okay.
Viewers, today we have discussed some interesting properties of determinants, and we have defined adjoint of a matrix, and we have seen how this can be used to evaluating inverse of a square matrix. Thank you.
Thank you.